So again, we've got our confidence interval basics. 95% is what we usually do. That's a z-score of 2. Just want to double check that in StatKey. Reset my plot here. So here I have my normal distribution, and I have a mean of 0, standard deviation of 1, which means I'm doing z-scores. I'm going to throw a 2 tail, and StatKey is going to say, hey, let's put 95% in the middle. Cool. And if I look down, StatKey says the actual z-scores are 1.96 and negative 1.96, which are close to 2, but not exactly 2. So that 2 standard deviation rule, that 95% rule that we started way back in chapter 2, I think it was chapter 2, is it chapter 1? 1 or 2, is an estimate. It's not exactly, it's just close. If I switch this lower bound to a z-score of exactly 2, right, that's going to push it out to the right and out to the left a little bit. I should get a little more than 95% in the middle. So if I pick a z-score of exactly 2, it turns out I get 95.4% in the middle. That 2 standard deviation rule is just an estimate. It's not exact, but that's okay. It's close enough for most circumstances. But sometimes we want to be more than 95% confident in our interval estimates. So we might want to be 99% confident. In that case, StatKey says, well, then you should pick a z-score of 2.576 to be 99% confident. And then we just need to know, okay, if the z-score is that, what's the spread? What's the standard deviation I use? And that's called standard error. And that is this formula right here. So given a confidence level, we can then calculate a z-score. If we're also given standard error, then we can make a confidence interval. Let's try it. All right, so here I got a new situation. So this is a problem you saw in the homework a couple of weeks ago. We are interested in finding the mean water temperature of a river during the spring runoff from the nearby mountains. You must estimate the mean temperature in degrees Fahrenheit with the following sample temperatures. So I have some sample temperatures off to the side here. And I already calculated the mean of the sample. That came out kind of weird, that bar is supposed to be over the x. So I have, 25 different water temperatures that were measured on this particular river. And the average temperature of those 25 is 43.384. Standard deviation of these guys over here is 4.72. What's more important to me than the standard deviation of the sample is the sampling error for all possible samples of size 25, because that's what I need to make a confidence interval. That's why we went to StatKey to run a simulation based on data like this. So 2 weeks ago, I would have copied and pasted this data into StatKey and ran thousands of samples of size 25. This time I'm going to do a little bit different because I have enough information to do this on the screen already without using these numbers again. So important things for doing a confidence interval: start a sketch. Draw your best symmetric bell-shaped curve. In the middle for a confidence interval is our point estimate. So we're saying that in general, this time of year in this river, you should find water temperatures of about 43.384. So like on the Umatilla River where I live, that would be like February temperatures probably in the Umatilla. Where are we now? We're in May. Temperatures now are probably in the 50s in the Umatilla, and they're just gonna get warmer. All right, so right in the middle goes my X bar. That's the 43.384. That's like having a z-score of 0. I want to be 99% confident, so I want to look for 99% of other samples of size 25. So that's where I incorporate the standard error with this 99%. So 99% is going to be out near 3 standard deviations. So this would be like 1 standard deviation, 2, 3, oops, z-scores, that would be about -3 there, about 1, 2, that would be a +3 for a z-score over there. Now, for a confidence interval, I don't just need the z-score, I need the temperature, the average temperature to go with it. I want 99%, and we just saw in stat key that that's about right over here and over here, a little over 2.5. So I'm looking for 99% in the middle. So my confidence level here is 99%, which is a decimal is 0.99. My alpha for the tails, would be 1 minus that. So 1 minus 99% is 1%. And the tails get to split that. So if I take that 1%, divide by 2, that gives me 0.5%, or as a decimal, 0.005. Right? 0.01 is 1 whole percent. I want 1/2 of that. So that's over here, my alpha over 2. Oops. And if I was using a spreadsheet, I definitely want to know that. But stat key automatically gives me the right numbers. Now, stat key, to find the correct z-score to go here, that's what I need next for my formula, is I just go to the stat key and I say, hey, I want 99% in the middle. I'm on the theoretical normal distribution here. I just put 99 there, 0.99 as a decimal. Stat key says, okay, your z-score, your critical z-score is 2.576. Notice the other one is just the opposite of that. So according to stat key, critical z-score, book calls it z star, is 2.576. So that's this guy right there. On the other side, negative 2.576. Now, what I want to do is I want to use the z-score and the standard error to jump to find out what's my upper. So my upper value here, starting in the center at 43.384, I want to add this standard deviation this many times. So x bar plus the critical z-score times the standard error. So that would be 2.576 times 0.944, the spread of the sampling distribution. Similar on the other side. On the other side is that mean, but go left. So subtract that special z-score times the standard error. So that would be 43.384 minus 2.576 times that spread for the sampling distribution, 0.944. So let me go about a calculator and do it. This in a spreadsheet, because there's a whole bunch of things to do there. So let's just modify this one right here, a new tab. I'll reshare this. So this is my confidence interval. I'm just going to call it CI down there at the bottom. All right, things I need to know for this. I need to know the confidence level. So I was given that. So that would be that 99%. And spreadsheets are nice. I can just type a percent. And let's see. So that was given. Let's highlight that. And based on that, I can get the tail probability, which I need if I'm going to have the spreadsheet do anything for me. So alpha. So often on a spreadsheet, I document my work like I do on paper, would just be take that number above from 1. So 1 minus that gives me that 1%. Alpha over 2 would just be equal to the above number over 2. So just some setup there. Other information I need to make this happen is I need the sample data. So I need the mean from the sample. Now I was given the sample STD, I'll just call that sample S, but what I really, really want is the standard error. That's more important. So my mean was given, I don't need to recalculate it, 43.384. So this week I'm calculating a lot of stuff for you ahead of time. 43.384. 43.384. Then I need those other two numbers, sort of. We'll use this next week. 472944. Ooh, typing. And again, given stuff, let's highlight. You should come back to this later. All right, so other things I have to calculate. So based on this alpha right here, or the confidence level, either one will give me similar results. I need that z-score, so I guess I'll throw that in here. And I'm just gonna put stat key gave it to me. I'll show you how to do it on the spreadsheet in a sec. 2.576 or 567? 576, okay. And so now, based on all that stuff right there, I can calculate that lower and the upper. So lower and upper for my confidence interval. So remember, to get the lower, we always start at the mean and then subtract the margin of error. So, and I'll show you the margin of error in a second. Why? So mean minus our special z-score times the standard error. And no, I don't want to autofill. So Google says that's about 40.952, depending on how many decimals I needed. Since this mean has 3 decimal places, I'd be tempted to go 3 or 4 with that. So maybe I'll knock it down. Oops, wrong way. Let's go 4 decimal places for fun. And then upper is start at the mean and add your special z-score times your standard error. Is our formula there. Now, think about this for a second. Let's go back. We could find the margin of error based on these two, but we actually already have it in our picture, sort of. So from the middle, if I jump over to the right, that distance is the margin of error, that number I add, or the number I subtract. So it turns out this z-score times the SE, this right here, that's my margin of error. So it's kind of a new formula we get to add to our tool belt. The margin of error is always going to be that critical z-score times your standard error. You just got to get that standard error. Before, we were relying on stat key to simulate it. Now I'm just giving you the standard error, and there's 2 ways we can get it. We can use this theoretical formula I'll go over next week, or we could have stat key simulate it. And for this one here, I used a theoretical formula I'll talk about next week. For now, I'm just going to give it to you. So that's the margin of error. So I actually already have the margin of error just by taking this z-score and the standard error into account. So I'm just going to add, say off to the side here, the margin of error is equal to my z-score times my standard error. Before, we were getting it by subtracting these two and divided by 2, so I could double check that over here. Check on that idea. The subtraction has to happen first, so I need parentheses, upper minus lower, those parentheses divided by 2, and notice it's exactly the same number. If I want stat key, I use stat key to find this number right here. If I wanted the spreadsheet to find that z-score right there, that's this idea of the inverse probability, which requires a left tail, which is my alpha over 2. So I can actually check this on the spreadsheet. So I'm just going to double check z-score spreadsheet. So in this case, I'm given a probability and I want to find the z-score. So that's the inverse normal. Start typing normal, see what options we want, and we just want to use the dot version mainly for compatibility with Excel. And it says, what's the x value? In this case, the x value is the tail probability, comma, this is a z-score, mean is 0, standard deviation is 1. And the spreadsheet is going to give you the -1 because I gave it the left tail probability. Z-scores are negative on the left. And notice that matches to the nearest 1,000 what Stacky gave me. All right, in case you missed this spreadsheet, I'm going to reshare it.